Okay, general relativity step by step. I'm going to talk about curvilinear coordinates, curvilinear coords. We've got our nice Cartesian coordinate system. I'll just give you the general picture. I'm just going to switch to red here. We've got this beautiful Cartesian coordinate system. This is, of course, lines of equal y equals 0, y equals 1, y equals 2, y equals 3. I'm colour coding it because things get a bit messy and it gets a bit difficult to see where you are. Not perfectly accurate, but it'll do. That's, of course, lines of x equals -1, x equals 0, x equals 1, x equals 2, x equals 3. Now, this is a beautiful, beautiful, beautiful system here. The Cartesian system is far simpler than it's got any right to be. All the coordinate lines cross at right angles, and they all move at the same... as you increase x, it moves at a uniform rate. So let's just have a look at the general system here. So I'll draw the lines of constant. It can't be called y, I'll call it something else. These are notionally horizontal, but you can see that they're wibbly-wobblying about. And instead of x and y, I'm going to call it a and b. So I guess these are lines of b equals -1, b equals 0. This line here is b equals 1, b equals 2, b equals 3. And I'll switch to blue for the x's. And of course, they're going to be a terrible mess. And that's a equals -1. This line here is a equals 0, a equals 1, a equals 2, a equals 3, and so on. So going back to, so why is it so bad? It's bad for lots of reasons. If I go back to black, it's some of the lines cross at right angles, but some of them you'll see here. This line here crosses at and this one here. They don't cross at right angles at all. This is a non-orthogonal. If I write it down, non-orthogonal system. Now, if you can use an orthogonal system, you probably want to, but sometimes you can't. So that's one reason I want to give you an example of a non-orthogonal a non-orthogonal coordinate system. But also it brings out lots of details and lots of, well, I won't say subtleties, but it shows the great power of tensor notation, and it shows how clever tensors really are. So I quite like it. The example I'm going to use is not this one. This is an arbitrary one, of course. This is just an arbitrary one. Coordinate system. So what I'm going to do is I'm going to cook up. I'm not cooking it up. I'm just going to draw it out. We've got x's and y's here, of course. Blong, 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 blong. But instead of x's and y's, I'm going to draw. We're going to have what I call h equals -1, h equals 0, h equals 1, h equals 2, h equals 3, h equals -2. And then the equivalent of the red lines is actually going to be indexed by the angle it makes with the origin. I've also got difficulty drawing it accurately, but I'll do my best. There it is. And that's, of course, theta equals 0. Theta equals, looks to be about pi by 3. That's pi by 2. Sorry, that's pi by 6. That's pi by 4. And so forth. Theta is increasing in this direction. So we've got this nice little system here, and I'm just going to write out, this is, of course, what colour am I on? That's red. So that's these are lines of y equals 3, y equals 2, y equals 1, and so on. And these blue lines here are x equals -1, x equals 0, and so forth. So what's the relationship between these two guys? Well, we've got this sort of very nice little sort of right-angled triangle. That angle there's theta. This is x, which is of course equal to h, and that's y, which equals h tan theta for this point here, this point P. So let's just write it out explicitly. Actually, I'll do the forward one first. H equals x, and theta equals arc tan y over x, which is this angle here, which is y over x. That's the forward transformation. And the backward one is x equals h, of course, and y equals h tan theta. So what I'm going to do, I won't do it on this screencast, I'll do it on the next one, is to derive the Jacobians for the forward and backward transformation, just so we can get a feel for how the tensor transformations for the general curvilinear coordinate system on non-flat spaces work. So I'm going to stop there. It's already been longer than I wanted. This is over 5 minutes, and I don't like that. And I'll derive the Jacobian in the next screencast. I'm going to stop there.